Okay, this time we're going to be talking about something called the ideal gas law. And the ideal gas law is really an interesting thing because what we do is we take all of those gas laws that we talked about and we think about it from a perspective of what would happen if they behave exactly the same way all the time. So we've got to take a look at the kinetic molecular theory to be able to understand what's going on there. So the assumptions of the model, remember, all particles in constant motion, random, and they're always in motion. The collisions are perfectly elastic. Nothing sticks together ever. Okay, the volume of the particles in the gas doesn't matter. They don't have very much volume, so it's not even something we're going to consider. And the average kinetic energy of the molecules is the Kelvin temperature. This theory neglects anything about intermolecular forces. So if there's polarity in something, it's not even talking about that. It doesn't care about that. And it's important to note that gases fill their container. They expand. And they can also be compressed. So we can change gases in a way that we can't change solids and liquids. So this is just something that we were talking about before. So in an ideal gas, oops, sorry, it's not working very well. So at normal conditions, such as standard temperature and pressure, that's 1 atmosphere and 25 degrees Celsius, most real gases behave like an ideal gas. So at low temperatures and low pressures, things are behaving more ideally than they would be if there are high temperatures or high pressures. So, we can kind of make this assumption. So many gases like nitrogen, oxygen, hydrogen, and noble gases behave, and some heavier gases can be treated like ideal gases within reasonable tolerances. In other words, we are making some assumptions that's not exactly true, but because of what we know, those assumptions make very little difference in the end of what's really happening. And we'll be talking about that in real gases a little bit later. So generally, gases behave more like ideal at higher temperatures. Generally gases behave more like an ideal gas at higher temperatures and lower pressures. So if we get them really hot and we get them in a low pressure, they behave more like ideal gases. But at standard temperature and pressure, they're behaving relatively ideally. Okay, so when we expand the temperature, when we increase the temperature, the intermolecular forces become a less significant part of what's happening. So we know as we decrease temperatures, intermolecular forces, those particles getting closer, have more to do with one another, and they're going to have more attractive force. But if we speed those molecules up, we know that they don't. So it's really important to think about those assumptions that we're making and why we're making them. And of course, the size of the molecules becomes less significant when we have them at higher temperatures because there's a lot more empty space between them. So the size of the molecules doesn't matter as much either. So an ideal gas is expected to have a constant value of pressure and volume as we go across. So we can see that, carbon dioxide behaves less ideally than neon and oxygen does. Much less. So carbon dioxide is kind of not as ideal as we'd like it to be. So we can see that from that. So why does carbon dioxide deviate the most? Well, carbon dioxide has the greatest mass. It has more electrons. Therefore, there's more interaction, more intermolecular forces, more London dispersion forces. So there are lots of things going on here. And remember, if we've got a larger gas, it's going to behave less ideally because it's got more forces to have to counteract. And so oxygen and neon doesn't. They don't have as many electrons. They don't have as many things to go against. So some gases are stickier than other gases is what we're trying to tell you. Okay, so the ideal gas law. So we have 4 quantities, remember, that describe the state of gases: pressure, volume, temperature, and number of moles. So if we combine all of the gas laws together, all 4 gas laws together, we get that volume is directly proportional to the number of moles divided by temperature, or times temperature divided by pressure. So we can replace this proportionality with a constant. So if you can go and calculate for a constant, you can replace the proportionality with that constant and make an inequality. So we get this constant R, which is called the gas law constant. And so we get the ideal gas law of PV is equal to nRT. So whenever we replace a proportionality, we have to have a constant that helps us to make that equal. And that's what the R, ideal gas law constant, will help us do. So we get this idea. We've got all of these laws, we're combining them all together, and we can see that here we have PV is equal to nRT, and we can see what's happening here. Okay, so the ideal gas law is an equation of state. R has different values. This happens to be the value of R in liter, atmospheres, moles, Kelvin. You'll notice that the unit is related to the four things that are going into it. Another one that we use quite often in this class, because we use torr and millimeter of mercury quite often, is this value, the value of 60, is it 62 or 63? I'm having to look here. Hang on one second. I thought I had it in my head and now it's flown away. It's flown the coop. I know I did it though. There it is. It's 62.363. And the unit is liters, torr. Remember, torr can also be millimeters of mercury per mole Kelvin. So the only thing that changes there is the pressure unit. So you have to make sure that you know what your pressure unit is before you decide which R to use. So this is also R. This is R. It's just R for a different unit. So this one could be used for millimeters of mercury or torr. The other one used for atmospheres. Those are the most common that we use in chemistry. Very rarely do you see pascals or kilopascals, but if you do, I would change them to atmospheres or torr and use one of the numbers that I know is on your sheet. It is on your cheat sheet, the equation sheet that you have for your test. So this is useful at low pressures and high temperatures. Yeah, this guarantees you points on the AP exam. If you know it's a state equation, if you know it happens at low pressures and high temperatures, you're good to go. Okay, so exercise 1. This is where we get into working some things. So here we go. A sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres. Calculate the moles of H2 molecules present in this gas sample. So let's look at what we have. We know that we have V. V is equal to 8.56 liters. I can't write today. We know that T is equal to 0 degrees Celsius, which is 273 Kelvin. You notice I automatically just do it. P is equal to 1.5 atmospheres. And N is what we're looking for. We're looking for N. So we come over here and we see that PV is equal to nRT. So we divide both sides by RT. And we get N is equal to PV over RT. So we start plugging in. We have 1.5 atmospheres, 8.56 liters. We have a temperature of 273 K. And because we have atmospheres, we are going to be using 0.08206 liter atmospheres, moles, Kelvin. Kelvin cancels out, atmospheres cancels out, liters cancel out. So now we just have a plug and chug problem. A plug and chug. So now that we've put all our numbers in, now it's simply a multiplication division problem. Just make sure that you're always using parentheses here because you have more than one quantity on the top that's divided by more than one quantity on the bottom. Just make sure you're using parentheses when you do this. So when we get this, our answer is 0.57 moles of H2. That's our answer. Pretty simple. Okay. Now, this one says which gas law? So that means they're going to be testing us a little bit. And remember, all of the gas laws are combined to form the ideal gas law with these ideas of assumptions that we're going to be using, which kind of gets rid of some things. So suppose we have a sample of ammonia gas with a volume of 3.5 liters. So we have volume of 3.5 liters. We have a pressure of 1.6 atmospheres. The gas is compressed to a new volume. So we've got a volume 1 and a volume 2 of 1.35 liters at constant temperature. Use the ideal gas law to calculate the final pressure. So I want P2. All right, so I have a P1, I have a P2, I have a V1, I have a V2. So this is Boyle. This is Boyle's law. So we could use PV equals nRT, but there's no reason to. Just go straight to Boyle's law. That is P1 V1 is equal to P2 V2. Okay, we've got the sample of ammonia gas, which doesn't change. That means the number of moles doesn't change. The temperature is not changing. And the gas law constant is going to cancel out, so it doesn't really matter. So we're looking for P2, so we're going to divide both sides by V2. And we get P2 is equal to P1 V1 over V2. So we plug in. We've got 1.68 atmospheres times 3.5 liters divided by 1.35 liters. Now, if we remember the relationship, they're opposite. So the volume went from high to low. So we already can predict that the pressure should go, up. And in fact, the pressure goes up significantly. We get 4.4 atmospheres. That's what we get, okay? So I'm going to skip over a couple of these, and I'm going to go to problem 12. So you guys can do problem 10 on your own and problem 11 on your own. I think you're capable of doing those. Remember that you're just having to look at some of them. Make sure you're thinking about the gas law that you can use instead of PV equals nRT. Okay, so here we go. 12, a sample containing, we've got a number of moles, N is equal to 0.35 moles, okay, of gas at a temperature T is equal to 13 degrees Celsius, which is 286 K, okay, and there's a pressure of 568 torr, so high pressure. And we know that it is T2, it's heated to 56 degrees Celsius, which is 329 K. And the pressure goes to 897 torr. All right, so calculate the change in volume that occurs. So in reality, we really need to figure out part of this. So we want to know the change in volume that occurs. So we have to figure out volume 1 and volume 2. And the way we figure out volume 1 and volume 2 is we use PV equals nRT. We've got to figure out the volume. So if we have PV is equal to nRT and we rearrange it, we know that V is equal to nRT over P. So you can do situation 1. So V1 is equal to 0.35 moles times 60, oops, go back, times 62.363. Remember, torr, liters, moles, Kelvin, times, I've got to put that one up here, times T is 286 Kelvin, divided by P, which is 568. And what we get, we get V1 is equal to 0.09099 liters. So that's what we got right there. So now that I've got that, this becomes a combined gas law problem. And I'm looking for V2. So I'm now looking for V2. I have V1. I had everything that I needed to figure that out. I could also do this another way. I could also find out what happens to V2 here using the same number of moles. So I could do the same thing. So I could figure out V2 is equal to 0.35 moles times 62.363 torr, liters, moles, Kelvin times 329 K divided by pressure of 897 torr. Okay, so we've got to calculate that. And I didn't do that ahead of time, so I'm a bad person here right now. Okay, so we get 8.01 liters. So the change in volume in these two situations is 8.01 liters minus 0.9099 liters. Okay, so we get a change in volume of 7.91 liters. And that would be your change in volume that occurs in this system. Okay, so this is beautiful because the ideal gas law gives us a way to do stoichiometry with gases, because now we have a molar relationship. We can calculate the number of moles, and we can calculate the number of moles in situations that are not at STP. So we always knew at STP it was 22.4 liters of gas in 1 mole. But now we can work it without being in STP and find out the number of moles and then work backwards. We just have to be really, really careful about what we do. So here's our first example of gas stoichiometry. A sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of N2 are present? Again, this is dead easy. We already know how to do this. So we have 1.75 liters of N2. And we know we're looking for moles of N2. So we've got liters, we've got moles. We know there are 22.4 liters at any 1 mole of gas at STP. So we've got liters going away, we've got moles, and we get an answer of 0.0781 moles. Pretty simple. So we can use any method that we need to. We can do it any way we want to. That's beautiful. We have lots of different choices. Okay, so here we have another one. Quicklime is produced by a thermal decomposition of calcium carbonate. Calculate the volume of CO2 at STP produced from the decomposition of 152 grams of CaCO3 by the reaction. Okay, so again, we're at STP, so we can just use our simple stoichiometry. We just need to make sure we have a balanced equation, 1Ca, 1Ca, 1C, 1C, 3 O's, 1, 3 O's. So we're good. It's a balanced equation. So now we take 152 grams of CaCO3, and I want to know eventually liters of CO2 at STP. Okay, that's what I want to get to. So I've got to do some converting. Okay, so the first thing I need to do is I need to get rid of grams of CaCO3 and go to moles of CaCO3. Well, I calculate it's 100.09 grams to 1 mole. Then I can see I have 1 mole of CaCO3 to 1 mole of CO2. Okay, so CaCO3 is gone, grams are gone. Now I have moles of CO2 to liters of CO2, and that's 22.4 at STP in 1 mole. Moles are gone, and my answer is 34.0 liters of CO2 at STP. You just have to be quick when you're doing those problems that are going to involve things on your multiple choice. That's all you have to be thinking about. Okay, so next, a sample of methane gas having a volume of 2.8 liters at 25 degrees Celsius and 1.6 atmospheres was mixed with a sample of oxygen gas having a volume of 3.5 liters at 31 degrees Celsius and 1 atmosphere. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.5 atmospheres and a temperature of 125 degrees Celsius. So this is a lot more complicated, but we can still do this. It's not a big deal. What we first have to figure out is the number of moles. So we know we have a chemical reaction. We know the chemical reaction is CH4 plus O2, and we know that that's yielding CO2 plus H2O. So we go and balance that. We've got 1C, that's good, 4 H's, 2 H's, so we could put a 2 right there. O2, that's 4, so we got to put a 2 right there. So now it's balanced. So we have a balanced chemical equation, but the first thing that we need to figure out is how many moles of these things do we have right now? So that's where we have to go back to PV equals nRT. So I'm going to write the equation up here. I know PV is equal to nRT, and I know that N is equal to PV over RT. So that's the equation I'm going to use. I'm going to find the number of moles of all of these things. So that's what I'm going to be working on right now. So P for the first one is 1.65 ATM. The V is 2.80 liters. R is 0.08206 atmospheres, liters, moles, Kelvin. We're at 25 degrees Celsius, so we're at 298 K. So we get that we have 0.1889 moles of methane, CH4. So I'm going to put that right here, 0.1889. So that's my initial concentration of methane. So how about oxygen? I'm going to do the exact same thing for oxygen, but my numbers are going to be a little different because oxygen was at 35, but it was 35 liters, and it was at 1.25, so 1.25 atmospheres, and there were 35.0 liters. And we still have the same R because it's the same unit of pressure. Okay. And then the temperature was 35. So that's another 20. Is that right? Temperature, no, the temperature was 31. So 31 degrees Celsius is, let's see, 6 degrees more, so that would be 304. Okay, 304. Okay, so we have 1.25 times 35 divided by 0.08206 times 304. And we get 1.7 1.75 moles of O2. So we have 1.75 moles of O2. We have none of either of one of these things. So we know the change, remember this is our limiting reaction, since we have two different quantities of reactants, we have to figure out which one runs out. So we know the change for methane, there's only 1 mole, so it's minus X. We know the change for oxygen is minus 2X. We know the change for carbon dioxide is plus X. And we know the change for H2O is plus 2X. Okay, that's actually going to be helpful later on. All right, so we know that we have 0.1889 minus X. We have 1.75 minus 2X. So X here is 0.1889. X here is like 0.8 something, which is much bigger than 0.1. So our limiting reactant has to be the methane, which means we make 0.1889 moles of carbon dioxide. So now that we know the number of moles of carbon dioxide, we can go back and look at what we're looking for. We're trying to calculate the volume of carbon dioxide at these particular conditions. So let's go back to PV equals nRT. We're not going to use this equation anymore. We're going to solve for V. So V is equal to nRT over P. So we're going to plug that in. So we've got N, which is 0.889 moles. Okay, we've got R, which is 0.08206 atmosphere, liters, moles, Kelvin. We've got 125, which happens to be 398. And then we have a pressure of 2.5 atm. Okay, so atm cancels out, Kelvin cancels out, moles cancel out, leaving us with liters, which is always great. And we end up with 0.405 liters of CO2. That's the answer. So yeah, are there lots of steps here? Yeah, but it makes it possible. Before we had no way of being able to do this. And now we have a way to do this. It's amazing. Okay, density. Density works here because remember, density is equal to mass divided by volume. Hang on, that's pretty familiar. Volume is in the solution. So if I think about what density is, mass divided by volume, and I think about what N is mass divided by molar mass, and I start like interpreting what that is, what I end up with is I can find the molar mass of a gas because the molar mass of the gas is equal to MRT over VP, but MV, M over V is equal to density. So I get this idea that molar mass is equal to dRT over P, or dirty P. Molar mass is equal to dirty P because chemistry kitties cover up their P. Yeah, exactly. So if you can remember dirty P, you've got this, dRT over P. You got this. It's great. Okay, so let's look at a problem. So molecular mass or molar mass, kitty cat, all good cats put dirt over their pee. Yeah, it's crude, socially unacceptable. It is, but you'll remember it. And you'll thank me later for it because you'll be flying through problems and you won't have to worry about it. You do have to remember though, that gases have densities of grams per liter, which makes sense because our units of gas volume are usually in liters instead of grams per milliliter. We're not talking about a solid, we're not talking about a liquid, we're talking about a gas. And so the bigger volumes of gas are going to be in grams per liter. So just make sure you keep an eye on your units. Okay, so here we have the density of a gas was measured at 1.5 atmospheres and 27 degrees Celsius and found to be 1.95 grams per liter. Calculate the molar mass of the gas. Well, we know that the molar mass is equal to dirty P, right? So now we just plug stuff in. So we have 1.95 grams per liter times R is going to be 0.08206 atmosphere liter mole Kelvin. Okay. T, 27 plus 273 is 300, yeah. 300 Kelvin. Okay, and then we're going to divide that by 1.50 atmospheres, the pressure. So pressure goes away, Kelvin goes away, liters go away, and we're left with unit of grams per mole. That's good because that's what we want, grams per mole. So then we just now do the math. So we have 32.00 grams per mole. That's pretty much it, young people. If you can do those things, you got this. You got gas laws. You got gas stoichiometry. It's not a big deal anymore. You're going to be great at this. It's going to be awesome.